In this lecture, the main topic is the chain rule, and there are two cases. The first case, we have a function that depends on a bunch of variables, and all these independent variables actually are functions of another variable. Okay, that's our case one. So say f is a function of two variables, x and y, and we call the dependent variable z. So z equals f of x, y. And x and y are actually both functions of only one variable, t. Okay, so x equals g of t and y equals h of t. Then z actually only depends on t. Then dz dt actually is partial z partial x. Notice that z has two variables, so you have partial derivative. Dz dt equals partial z partial t, then dx dt, then plus partial z partial y, dy dt. Okay, and here I sort of said it without stating the definition. A differentiable function. What a differentiable function is? Well, what does differentiable mean? This differentiable essentially means partial derivatives fx and fy are both exist and continuous near the point that you are looking at. Again, I'm trying to avoid the epsilon delta kind of definition. That's why I can't really give you the precise definition here. But let's just say when functions are nice, they are fine. The second remark is when you have a function that depends on three variables, then my three independent variables will be x, y, and z. Then my dependent variable, I'll call it w. Then what happens is w depends on x, y, and z altogether, but all of them only depend on t. So w is a function of t. Then the chain rule is dw dt equals partial w partial x dx dt plus partial w partial y dy dt plus partial w partial z dz dt. Okay, so pretty much this is the situation. You have a function. Let's forget about the name of the output, just call them f. Okay, your f has maybe x and y independent variable, well, maybe z, maybe even more, and then what's the next? Oh, w is taken, well, let's use w. Then each of them is a function of t. Then you just do this pass plus this pass plus this pass plus this pass. Okay, so partial f partial x, then x and t, you only have one function, dx dt, pretty much. Then you add them up. Okay, that's multiplication. And when you make it into only one function, that's our old case. Our f is a function of u, and u is a function of x. So you have df dx is df du times du dx, which is here. Okay, when you only have like one pass. If you have multi-pass, you just add them up. Okay, let's see our first example. I'm having z equals xy third minus x squared y, where my x equals t squared plus 1 and y equals t squared minus 1, and I'm looking for dz dt, and the z depends on x and y, so it's z depends on x and y, so partial z partial x, then dx dt plus partial z partial y dy dt, where my partial z partial x equals y third times derivative of x, which is 1, minus y times derivative of x squared, 2x, times dx dt, 2t, plus the same function but differentiated with respect to y. I'm having x times 3y squared minus x squared, differentiating with y. So y is times the derivative of dy dt, that's another 2t. So if I put 2t together, I'm having 2t times y third. This is minus 2xy. Then I'm having plus 3xy squared minus x squared. Okay, that's the chain rule. It's just that you have more than one path to go from f to t. You need to add all these paths, which are sort of the product of two derivatives, partial derivative or regular derivative together. Case 2, if your function is a function, multivariable function, and then each of the independent variable here are also a function of multivariables, but they share the same variables. Then, you sort of are doing the same thing. It's just that you can't take derivative of f with respect to s and t at the same time in one round. So it's the same thing. You have f up here and you say you have x and y. It's just down here. You need to choose the variable that you are going to. If you are going to say partial f partial s, you put s here, then you go this way. This will be partial f partial x partial s plus partial f partial y partial s. Okay, and then each pass is a multiplication and you add them together. Then you start over to do it with another variable. Remember, your f depends on x and y. X depends on s and t. Y also depends on s and t. So at the end, your function f or the variable corresponding to f, which is g, depends on two variables, s and t. So you can start over another round with, just s or t. So t here. Then you do partial f partial x partial t plus partial f partial y partial t. Or here, actually, instead of using partial f as a function, I use the partial z, okay, as the variable. But that's the idea. On each pass, you have a product. If you have another variable z, then you get another pass. You just add them together. Notice here the variable down here, s or t, are called independent variables. The variables that are in the middle, x, y, or maybe x, y, and z, are called intermediate variables because they sort of like sit in the middle. And at the end, up there, the f or the variable z is called the dependent variable. So t, you come up with t, then x and y and z on one hand depends on t and s, but on the other hand also feed to the upper function z. Then z, which is function f, really is the dependent variable depending on x, y, x and y. No, here, so here I can have z in my original setup. Z depends on x and y, which depends on s and t. That's why z is called dependent variable. X and y, on one hand, they are dependent variable of s and t, but on the other hand, they are independent variable when you are looking at the upper level, z. Okay, so intermediate variables and dependent variables. You have 3 levels now. Let's look at example 2. I'm having z is a function e to the x times sine y, so 2 variables, where x equals st squared and y equals s squared t. So z depends on x and y both depend on s and t. Then we go back to z and s. So partial z partial s will be partial z partial x partial s plus partial z partial y partial s, where my partial z partial x here is sine y will be the coefficient, and then taking derivative of x, I'm taking derivative of e to the x with respect to x. I'm having e to the x times partial x partial s t squared plus start over partial z partial y, e to the x is the coefficient, derivative of sine y is cosine y, times partial y partial s. T is the coefficient, derivative of s squared is 2s. So I'm having, do I want to pull out? never mind. So I'll just keep it trig e, sort of the t and s, plus trig e times 2ts. Okay, that's my first partial derivative. Now the second one, partial z, partial t, will be z with the intermediate x, partial t, plus partial z, partial y, partial t. So partial z, partial x will be sine y is the coefficient, derivative of e to the x is still e to the x. Oh, by the way, when you are doing this kind of like partial derivatives where you have two independent variables, notice that they are the same. Okay, so you can just copy what you had up there. They're the same. Times partial x, partial t. This will be different. Partial x, partial t, s is the coefficient. The derivative of t is 2t, plus, you can just copy this, or you do it over, it will be the same. Ex cosine y is my partial z, partial y, times partial y, partial t, s squared. Same thing, I'm going to keep trig e and the rest, plus trig e, then the s and t. These are my partial derivatives. Okay, now you can pause the video and try your practice number 1 and number 2. Okay, implicit function theorem. We already have solved implicit function, like implicit equation. And then we do implicit differentiation to get certain derivatives. Now with the chain rule, we can look at them one more time. So if capital F as a function of xy equals 0 defines y implicitly as a differentiable function of x. So you have an equation of x and y, but somehow actually with this equation, y is a function of x. Then you can find dy dx. But how? Well, you have f of xy equals 0. You take x is the independent variable, but capital F has two variables. You take derivative with respect to x here. So you are going to have partial x, f, xy equals partial x of 0. Of course, that's 0. But on the left-hand side, what do you have? You have partial f, partial x, partial x, partial x. F depends on two variables, right? Plus partial f, partial y, partial x equals 0. Actually, partial x were just dx. This is 1. And dy dx actually is dy dx because y doesn't depend on another variable. So what you really get is f partial x plus f partial y dy dx equals 0, or dy dx, you move the f of x to the left-hand side, to the right-hand side, and divide by the coefficient. So it's negative f partial x over f partial y. Notice that dy dx, okay, it's backward. Similarly, if you have an equation of three variables where z is a function of x and y, this is a function of two variables, z depends on x and y. And again, we make it work, as in you have a neighborhood. You don't just have the point, you have a neighborhood where the equation is true and the derivative is not 0. Okay, those are like the nice conditions to make everything work. Denominator not equal to 0, etc. So we do the same thing. We do our chain rule on our capital F equals 0. We take derivative with respect to, well, since you have partial derivative, now you can choose x or y, depends on which partial derivative you are looking for. So say x, I'm going to do partial x on both hand sides. This will give me partial f, partial x, equals 0. But no, sorry. I'm trying to take derivative. I don't think that's the right notation, okay? I'm trying to do this. So what happens is that we are going to have the fx, well, still let me do the partial f, partial x, partial x, partial x plus partial f, partial y, partial x plus partial f, partial z, partial x equals 0. You are taking derivative with respect to 0. And what you get is this is 1, this is 0, this is what you're looking for. And that is fx plus fz, partial z, partial x equals 0, or partial z, partial x equals negative f partial x over f partial z. Again, if you notice the same thing, okay, they are backward with a negative sign. Remember that you need the equation to be f equals 0. And then you take derivative with respect to the variable that you're looking at. Okay. Now let's see the example. You have seen this example before actually, but let's do it with another way. We are in this equation x cubed plus y cubed plus z cubed plus 6xyz equals 1. We want to find partial z partial x and partial z partial y, knowing that z is a function of x and y. Okay, so we need the capital F to be 0, so my f x, y, z will be x third plus y third plus z third plus 6xyz minus 1. And notice when I put x, y, and z, my capital F, they are all independent variable of f. So they are the same level, but actually x and y don't depend on each other, but z depends on both. Then I'm looking for partial z, partial x. That will be negative backward, okay? So f partial x, f partial z, where I just look at my function and take derivative. Fx is 3x squared. And now remember, they are all just same variables. So when you take derivative with respect to capital F, z is not a function anymore. Z is constant. So I'm having only the 3x squared from x cubed, and y cubed give me 0, z cubed give me 0, and this 6xyz term would give me plus 6yz. Negative 1, of course, give me 0. Then the denominator, f partial z, will be the 3z squared from z cubed plus 6xy. And I'm having 3 in both. I cancel it. I'm having negative x squared plus 2yz over z squared plus 2xy. Similarly, I can do partial z partial y. That will be negative f partial y over f partial z, and that is 3y squared plus 6xz over 3z squared plus 6xy. Dividing by 3, I'm having negative y squared plus 2xz over z squared plus 2xy. Okay, this will be a little bit easier. But essentially, actually, you have the same thing, but it looks a little bit, a little bit faster to get those partial derivatives. The the last topic in this lecture is a thing that we're going to, well, never mind, let's just do it. The directional derivative. Okay, so the directional derivative is, in this particular direction, how fast is f changing. So the directional derivative, you need to have a direction, which you want it to be unit. Very important, you want it to be a unit vector. Okay, so you have an f, and you have a unit vector AB, and your f at a certain point, at x0, y0, you shouldn't have the f. At x0, y0 in the direction of the unit vector AB, what happens is, because you have two variables, right? So the domain essentially is the whole plane. And when you move, you can change a little bit along the x-axis, you can change a little bit along the y-axis, or you can change a little bit along the vector they gave you. So you went that far. You went this much h on both a and b, two coordinates. So your x goes like AH above and your y goes BH above. And then you compare the new output and the old output, then you make h goes to 0. That's our directional derivative. So it is the derivative of f at x0, y0 with the unit vector u. So go back to our partial derivatives. We used to only change one coordinate, right? One x, only change x or only change y. And that would be, so if you remember, the derivative of x look like this. We are not changing y, but this is f partial x. Okay, we are not changing y, but we make x a little bit higher and see how it affects. So f partial x actually happens at the vector 1, 0, which is a unit vector. So f partial x actually is the directional derivative of f in the direction of the vector I, 1, 0. Similarly, f partial y is the directional derivative in the direction of j, 0, 1. And if f, again, is a differentiable function, the gradient of f is the vector function, which is called del f. Okay, del f is actually just f partial x in I direction and f partial y in the j direction. So this way you are saying I have f partial x on I and I have f partial y on j. So that's our gradient. And so gradient is a vector. It pretty much says along the unit vector, well, along the base unit vectors, okay, ijk or ij, the directional derivatives along each sort of axis is f partial x, f partial y, f partial z as a vector. And here's a very, well, maybe it's not that important, but it's kind of, it's very useful theorem. If f is a differentiable function of x and y, and f has a directional derivative in the direction of unit vector u, which is, the generic a, b, then the directional derivative of f at x, y, which is, again, general, along in the direction u is just f partial x times the x coordinate plus f partial y times the y coordinate, which actually is del f dot the u, dot product the u. Okay, so that actually is very important. What it says, what it does, it tells you when your x goes along that direction, your x and y goes along that direction, actually pretty much you're slicing the surface. Here's the picture. You have a function of two variables. The image will be a surface. You slice it. This time you're not slicing the surface with, by x equals a number or y equals a number. You are slicing the vector still a vertical space, but it goes also along the direction vector. So you slice it along, at this point, along that direction vertically. It will open up your open up your space with a certain curve. Well, I'm trying to shade it. Yeah, that's the curve at this point, remember? So then the directional derivative is the tangent, the slope of the tangent line, pretty much. Let's see this example. We have this function f of xy equals x squared y third minus 4y, a function of two variables. And we want to first find the gradient. So it's called del f. Okay, so del f is f partial x, comma, f partial y. We have only two variables. Or you can write f partial x I plus f partial y j. That's also okay. Different notations, same thing. F partial x, I'm taking derivative with respect to x, so y third is the coefficient times 2x, then minus 4y is constant, disappears after take derivative. F partial y, x squared is the coefficient, and then I have 3y squared minus 4. So this gives me 2xy third, comma, 3x squared y squared minus 4. That's my gradient of f. Second, I want to find the rate of change of f at 2, -1. In the direction of the vector b equals 2i plus 5j. The rate of change and the directional derivative are the same thing. Derivative is the rate of change. Okay, so we are having del f evaluated at 2, -1, and that would be this evaluated at 2, -1. I'm having 2 times x is 2, y is -1, comma, 3x is 2, y is -1, minus 4. So the x component is 2 times 2, 4 times -1 to the third power -1, so -4. And my y component, this is 12, take away 4, 8. In the direction of the vector b equals 2i plus 5j, notice that this vector is not a unit vector. We need to make it unit. So vector v has length square root of 2 squared plus 5 squared, which is square root of 4 plus 25, 29. Then my vector u, which will be a unit vector in the direction of v, is 1 over square root of 29 times, I want to use angle bracket 2, 5. So this is 2 over square root of 29, 5 over square root of 29. And then I dot these two. The directional derivative in the direction of u of f at 2, -1 equals -4 times 2 over square root of 29 plus 8 times 5 over square root of 29 this will be negative 8 over square root of 29 plus 40 over square root of 29, which is 32 over square root of 29. Okay, so that is the rate of change of f in the direction 2y plus 5j at the point 2, negative 1. Okay, that's it for this lecture. Now you can finish practice number 3.